Okay, now when we finished last time, we were looking at number 5. And on your homework for today, I asked you to kind of redo that because I hadn't given you a calculation scheme that makes sense of it. Okay? But in any case, you're going to end up with a graph. And what I saw, it was actually pretty good since I did give you a calculation scheme. Okay? And I didn't give you all the numbers. What I saw was often pretty good because I saw a lot of graphs that looked like this that apparently had this in the right place, okay, and apparently had the right coordinate here. Now let's just say that the coordinate here, the axis of symmetry, is at t equals 140, okay? Because that would be maybe a typical number that you get with the new set of instructions, which will be a lot like the set that you get if you get a problem like this on the test, okay? And the problems in the test are going to be, you know, pretty familiar if you've done the practice test to understand it. And yeah, what I saw, I'm not sure how many people are going to ace this thing, but it looks like most of you are probably in position to at least pass it. Okay? And hopefully you bring that up a little bit by Tuesday, okay? And pass it well. In order to make a D, do a good job of making the D. Try not to make a D. Try to make at least a C, hopefully a B or an A. Right? Okay. And okay, let's say that here you have y equals 80. So here's y, and here's t. Okay, so what did I ask you to do after this, and what could I ask you to do in this? Because there are other things I could ask you about this. Well, I could ask you, what are the coordinates of the vertex, right? Not sure that was on the practice test, but I could easily do it. So what does it look like the coordinates of the vertex are? Two coordinates of the vertex. One of them ought to be completely obvious, the other one you have to estimate.
140 and 20.
Okay, the t-coordinate is clearly 140. You're on the axis of symmetry. This is implicitly the axis of symmetry. I said it, I didn't write it. And that would be 140 seconds if it's in seconds, and y is in centimeters, right? And, okay, I think Riley said you want 20 centimeters. And 20 centimeters is reasonable here. Now, I gave you two coordinates. I think I labeled them D and E. Okay? So let's just say that D was 30 and E was 90. Okay? It depends on your algorithm and the letters in your name and stuff. But I think I gave you two coordinates, and I think they're between here and here. Okay? At least on the revised version that I'll ask you to do for today. Okay, well, I said do a fundamental triangle for the interval 0 to 30, the interval 30, 90, and the interval 90, 140, right? How are you going to do that? Well, it's real easy. Okay, you find the point for 30 here. And now you have the point that corresponds to 0 and the point that corresponds to 30, right? And I still see people making a fundamental triangle from some point here down to the x-axis because you're kind of confusing that you got an interval down here, right? And when you did that, I put a note on your paper that said you got to do 2 points on the curve. Your fundamental triangles for a curve go between points on the curve. They don't go down to the axis unless the curve happens to hit the axis at that point, okay? So So your fundamental triangle here is going to look like this. And I'll put this one here. You can draw it underneath, again, because there are two possibilities. I just chose to draw it on top of it, okay? And then you're going to have a fundamental triangle for the interval 30-90. And I'll make that one purple. Then you want to draw that triangle. People are not often big on actually drawing the triangle. Yeah, sometimes there's a faint dotted line that I can almost see. So I can see the triangle there, but I want the triangle to be nice and bold, okay? So I know that you know what you're doing, okay? And then on 90, 140, you're going to have, here's your 140 point, here's your 90 point. And try to, you know, I'm not doing a real good job of it. This isn't quite horizontal, and this wasn't quite horizontal, right? But try not to make the sides go off like this at a 45-degree angle or something, okay? Because it makes me uncomfortable as far as, you know, I want you to get it, and I'm not sure when you do that you really see where that fundamental triangle should be. Definition of the fundamental triangle is the hypotenuse goes between the 2 points, and the sides are parallel to the coordinate axes. And if you go here, your side is not parallel to this axis, it's not parallel to this axis, right? I don't expect artistic perfection, but try to make it at least good enough that I believe you wanted to make it horizontal or vertical, right? And if your artistic talents are as bad as mine, well, that's okay. If they're much worse, I'm worried about you though. Okay, make sense? Except what I just said. Okay, so I've got 3 triangles, and you know, just to make sure you understand which one is which, I've got this for this interval. I've got this one, darn it, for this interval. And I've got this one, hopefully purple will go over the top of the orange, for this interval, right? Okay? That's important. You have no idea how important it is. Okay? We interviewed a guy for the presidency on Tuesday. And turns out the guy's a mathematician and a former president. And he commented on calculus courses. He didn't talk a lot about it because I was the only mathematician in the room. But he talked about the conceptual approach they used in calculus at one of the schools he was at. He had the Harvard materials and said, yeah. He says, what you find is people come out of a calculus course and they don't know what a derivative is. Know what a derivative is? Slopes of these triangles, sort of. Okay? But people come out of a calculus course and don't understand the stuff that I'm trying to tell you about how to interpret a graph and a slope. A derivative is just something they follow a rule and calculate. Okay? That's not how you learn mathematics, and that's not how you learn the really important part of mathematics, which is the conceptual part. Okay, which is what I've spent the first third of the semester and what we're testing over. Okay? And then once we got the conceptual ideas down, we then hang the algebra on it and do a little algebra to understand more about the concepts. Okay? The most fundamental concept in calculus is a derivative, and that's exactly what we're doing here, except we're not doing the calculus of it. There's a little bit of difference. This is the average value of the derivative slope. This is the average value of what we call the derivative between here and here. Derivative point is the actual slope of a tangent line, which is close to this. If you understand that, great. And if not, that's okay. You don't need it yet. Okay? But that's the only difference. And some manipulation. Okay? I mentioned my grandson's at Virginia Tech in the engineering program. They're making him take calculus again because he took it as a sophomore in high school and didn't have college credit for it, even though he took the second semester of calculus, he's doing the first semester, and that's good because he's really going to learn what a derivative is. If he didn't learn that in my physics class, and if he didn't, might have to hurt him. He started to lift weights, so if I'm going to hurt him, I better hurry up to turn that around on him. Okay, well, seriously, but the comment he made went up for Grandparents' Day over the weekend. One of the first comments he made to me is we're doing epsilons and deltas. That's something you do in a very rigorous calculus course like we have at Tech to understand what a derivative is, basically. Okay? And an integral, which is not just the flip side of a derivative. He said the thing that surprised him is the problems that they're assigned are much harder than the problems they do in class. Okay? Now, I'm not doing that to you. I'll put a couple of problems on, usually on an assignment, that are harder than what you do in class. Okay? Just to stretch you a little bit and make you think. Okay? But most of them are just pretty straightforward extension of what we do. Just asking you to repeat what we did. Okay? I'm giving you very predictable tests. Okay? Just to see if you have these things, and then we continue to relate them to other things throughout the course. You won't know what that means until you get it. But you can expect when you transfer that if you're in any kind of a halfway challenging program, you're going to be a little more challenged at every level. You know, you're going to get something in class, and you're going to be more and more expected to build on it. Okay? So we're doing a little of that here, but I'm not expecting the kind of stretch that Virginia Tech expects in their engineering calculus course. Okay? Just giving you a little bit of a stretch. Whatever I think you can handle. Okay, anyhow, okay, that's a big digression. Okay, we're back to this. Do we understand what I mean by the slope corresponding to an interval? Okay, the fundamental triangle corresponding to an interval, then you have, of course, a slope corresponding to an interval. Okay? It's up here, it doesn't come down here. It starts above here, whatever the 2 points are. Okay? Okay, so let's just, I think I asked you to calculate a slope in one of them. So how do you do that? Well, to label a fundamental triangle, which is what you have to do to calculate a slope, you label the fundamental triangle. So let's label the purple one. Okay? So what are the 2 points? Well, can you estimate the coordinates of this point and this point? Everybody make their own estimate. I'll give you a hint. The first coordinate of this point is 30, and the first coordinate of this point is 90, right? What do you have to estimate? You have to estimate the y-coordinate. You see a scale here, okay? So, just accepting the numbers I have here, I think 20 is a little bit high for this one. That's okay, we'll still accept it because it's as plausible as 10. You know, if you're going to use 10 or 20, you can use 20 is probably the better one to use here, right? I actually think it's 14.893. Everybody see that? Okay. It's pretty obvious once I tell you, right? Okay, but 20 is okay. Not a bad estimate. Pretty close to halfway between 10 and 20. Almost rounds off to 20, right? Okay? Okay, well, anyhow, okay. What do you estimate the coordinates of this point are and the coordinates of this point? Okay, you've had time to think. What do you think the coordinates of this point are? Somebody tell me.
90.
Huh?
90. Can you move your finger real quick?
Okay, yeah, 90 what?
20.
Huh? Not 20, because you definitely have a slope between here and here, and you got 20 here.
I couldn't see because your finger was there. Maybe like 20.
What do you mean you can't see it? Just look.
23 maybe?
Yeah, I'll get out of the way. Okay, let me get my fat hand out of there. Okay, it's a little more than 20, right?
23.
Not much more than 20. You don't have much of a slope there. It's not that much above the crooked line that I used to project over to 20, right? Okay, but let's just say, okay, I don't know, what do you want to use, 90,
23.
23, that's what I was thinking. Probably need to get your head examined. You're thinking what I was thinking, it's scary. Okay, and what about here, 30 what?
45.
Yeah, it's a little over halfway to 90. It's not what I was thinking, so you may be off the hook there. But I have to accept that. It's probably better than what I was going to think. Okay? I was going to look between 20 and 80, and I'd have come out a little low. I might have come out with 40, but I like 45 better. Good job. Okay, so you got 90, 45, and 90, 23. Right? So now, what are you going to do next?
Draw the arrows.
Pardon?
The arrows.
Yeah, you're going to do arrows. Okay? So, you got to say what direction you're going. You're going from here to here. Now, if you want to go this way, that's okay. As long as you go this way when you go along this path. But I'm going to go left to right, basically. It's what we usually do. Okay, in polite society, you probably have little tendency to want to do it that way, but it's not wrong the other way. I had somebody do that, and they got it right, okay? Except when they did this, they didn't make this one negative, right? So it was good. I mean, the arrows were all consistent. You want to be careful. If you go this way, it's negative. If you go this way, it's negative, right? Okay? So then what are you going to do? Well, you're going to label this triangle, okay? So you're going to say the rise is 23 minus 45, which equals negative 22. Right? And the run is minus 30 equals 60. Okay? And then down here, well, I'm just doing the numbers. You really probably have an advantage if you put seconds on this one and centimeters on this one, so you're sure you know what you're doing, okay? But we don't have really room here, and you're probably going to draw your diagram too small to label it. I kind of didn't I? Okay? So sometimes follow my example, sometimes don't. Okay, so here, the slope equals rise over run equals, and then in a box, negative 22 over 60. Now you probably can't read the numbers because I made my diagram too small. Okay? Failure to anticipate. So you don't necessarily know what the numbers are, but you know how to put the numbers in. And you can look at just look at the class notes video. Get a 5-second view of this picture, and it'll be visible if you're not trying to see it on a tiny screen with bad eyesight. Okay? The screen doesn't have bad eyesight, but if you have bad eyesight, you don't want to see it on a small screen unless you're correcting your vision, right? Think about looking at it on a bigger screen, but you probably have really good resolution in whatever it is you're looking at. So if your eyes are up to it, you'll be able to see it. Okay. So the point is, you label the rise, you label the run, and you label the slope, and everybody knows how to do that. Not that you're always doing it, but you know how. How many times have we done it now? Okay? Then, you know, if you're on the test, okay, oh, dang, I made that too small. Let's go ahead and draw a bigger version so people in the back can see what I wrote. Now, in this case, I would write run equals 90 seconds minus 30 seconds equals 60 seconds. The little s there is not a little small 5, it's an s, standing for seconds, right? And rise equals 23 centimeters minus 45 centimeters equals negative 22 centimeters. So slope okay, we have negative 22 centimeters over 60 seconds, right? And then it doesn't hurt to do a decimal approximation. Of course, you're not going to have a calculator, but that's approximately, well, that's a kind of exactly point. Negative 0.367 centimeters per second, which you could theoretically do because you can do long division. That was not hard. Okay? And what's that tell you?
It's a decreasing slope.
Well, it tells you slope, but we're not talking about a slope. Okay, and this is another thing that I put several notes on. If you're interpreting something, telling me what it means, it doesn't mean the average slope between 2 points. The average slope between 2 points means something about the thing that's being observed. And this is water descending in a cylinder, right? Okay? So what's this telling you about the water descending in the cylinder, about the system? Okay? This is a representation of the system. This is not the system. It doesn't look like the system. Doesn't you see a cylinder here? See a stream of water? See any sharks? I mean, if you've got a cylinder full of water, bound to be sharks in it, aren't there? Okay? Sharks live in water, right? So if you got water, you got sharks. It's logical. Think about it. Okay. So, and no, there aren't sharks in the water comes out of the drinking fountain. Well, actually there are, but they're really tiny. You never notice. Okay. In the ocean they get bigger because there's more water. The drinking fountain is really small. Okay. Kind of in proportion to the volume that comes out of the drinking fountain as opposed to the volume of the ocean. It's a proportionality. Okay. So, I never know what I'm going to say. So what does this tell you about water in the cylinder other than maybe that you can't see the sharks?
Maybe that it's leaking out at negative 0.367 centimeters a second.
Not bad. What does 0.367 centimeters per second mean? What's it look like? How big's a centimeter? Show me with your fingers. Yeah, that's pretty good. Okay, about like that, right? A little less than half an inch. About 4/10 of an inch. Okay? Okay, so how big's 0.367 centimeters? Well, about a third of that, right? Okay, there we go. Okay? Now what does 0.367 centimeters per second mean?
Not much water is leaving the container.
Well, the amount of water that's leaving the container would be measured in volume, but you're right on the cusp of that. You know, I'd take that at this point as a good answer. Okay. But not quite. What does 0.367 centimeters per second look like? You can show me. Okay. Let's see everybody move their finger 0.367 centimeters. There, yeah, okay. Can you do that? Okay. Now, move 0.367 centimeters in a second. So, 1,001. Okay, there we go. So there's 0.367 centimeters, 1,001. Okay, so you saw my index finger move, didn't you? Okay. I should have said 15 meters per second, so I could show you how fast I am. Read an article about tsunamis yesterday. Tsunami that killed like hundreds of thousands of people in Indonesia back 6 years ago or something like that. I guess it's been close to 8 years. They said that outrun that thing, you'd have to be able to sprint like Usain Bolt, because they figured it was moving 11 meters per second. Okay? Well, top speed for Usain Bolt is less than 13 meters per second, I think. Might be 13. Depends on how he accelerates and stuff. Okay? So for me to show you the 15 meter per second sprint, I'd have to have a good night's sleep. Couldn't do that in an ordinary day, so I don't want to commit myself to that. Okay? 15 meters per second means, well, the length of this room is about 10 meters. Means he'd be from that end of the room to that one in 2/3 of a second. Okay? I can't do that from a standing start. I've got to have a head start. Preferably some kind of machinery, because obviously my legs won't do that. Okay. And the machinery, you can't trust at that speed, you can get killed, so I'm not going to do it. Okay. Now, 0.367 centimeters per second means you're moving this fast. It means water's going down at a speed that you can see, because you can see your finger moving 1/3 of a centimeter in a second, right? So that's what this tells you. That's how fast the water is going down. So you can visualize water in a cylinder, okay? And it's descending at a speed you can see. You know, after a minute it's going to be down about that far, okay? Whatever, okay? So it's a visible rate of change. When you get down to this one, it's a lot slower, right? When you get to this one, it's faster. So the water's slowing down, as you would expect. If water's leaking out of the bottom of the container, you get less pressure, the water spurts out less and less quickly. Everybody's got a leaky container somewhere that they observe every day or two, right? Yeah, okay, I hope so. I mean, you can't be physically literate if you don't do that. Okay, make sense? That's interpretation. It's not about points on the graph. The points on the graph represent something in the real world, okay? And you have to interpret it. So you have to interpret what centimeter over second means. And if you think about what's happening in the cylinder, the depth is changing in time, right? Okay, so you want to get kind of good at that, because you want to understand derivatives. Unless you do, and you want to understand what rates of change are, which is really what derivatives are. Okay? And of course, we're not doing the calculus of it, which is kind of window dressing once you understand what things mean. Pretty complicated window dressing, but understanding what they mean is harder than actually doing the calculus if you are pretty good with your algebra. Okay?